All right, good evening, ladies and gentlemen, and welcome to the Chesapeake Biological Lab Science for the Community lecture series. This is the last one of our 6 lectures for this autumn 2021 series. For those of you who are joining us for the first time, my name is Tom Miller, and I have the honor and privilege of being the director of the Chesapeake Biological Lab, part of the University of Maryland Center for Environmental Science. We've been offering these public seminars for a decade now, and in that time we have considered topics close to home, in the Patuxent River, in the Chesapeake Bay, and far afield. But the majority of our talks have been natural science talks. We've talked about the biology and chemistry, and on occasion the physics of the natural environment. Today is one of a few talks where we wander a little further afield and begin to talk a little bit more about social sciences, and in this case, economics. For those of you who've been following the Conference of the Parties in Glasgow, COP26, you may have heard of lots of expressions of hope, lots of expressions of intent to change. But you may also recognize that most of those expressions for change are accompanied by commitments of large sums of money to drive those changes. And I think as I think about our understanding of climate change, one of the most revolutionary changes that has occurred in the last few years is the increasing involvement of the marketplace, of economic systems, in evaluating risk and how those risks are changing in the face of climate change. And that's the topic of tonight, this final presentation in our Science for Communities series. We are giving this presentation as a Zoom conference, and that means that sadly you will not be able to unmute and ask a question. But if you have questions for tonight's speaker, please feel free to type them in the chat box, either during the presentation or at the end of the presentation, and I'll do my best to summarize questions and ask questions on your behalf of tonight's speaker. Before introducing tonight's speaker, a few words of thanks to our sponsors, Southern Maryland Toyota and Team Hyundai and PNC Bank, who have been underwriting this series for several years now and have been responsible for the advertisements we've been able to place in various media sources in support of this conference. And most of all, thanks to you, the audience, who have joined these sessions and asked so many penetrating questions at the end. It's a real pleasure to host these, and we look forward to a spring seminar series that likely will focus on the urban ocean as a theme. And we very much hope that those will be in person, and we will also maintain this hybrid setup for those of you who cannot come to the lab but wish to attend the conference virtually. So tonight, it is my very great pleasure to introduce one of CBL's own, Dr. Slava Lyubchich. Slava did his graduate work at the University of Orenburg in central Russia in 2008 for a master's degree, and in 2011 for a PhD in statistics. And from there, he moved to Canada on a postdoctoral fellowship supported by the Canadian federal government, where he worked on geographic systems and he worked on financial systems. That experience took him down to Texas, where he continued work on insurance risk. And it was from there that we were lucky enough to appoint him as an assistant professor in our new environmental statistics collaborative in 2016. And he came up for promotion and was promoted this last year, and so is now an associate research professor at CBL, and he greatly influences the analyses of the work that we do and the way that we think about our data. But tonight he's going to be talking about some of his own work on how risk is assessed in the face of climate change. So it is my great pleasure to introduce tonight's speaker, Dr. Slava Lyubchich. Slava, over to you.
Thank you, Tom. Let me share my screen. Is it okay? You can see the slides?
Yes, you can see the slides and we can hear you very clearly. Thanks, Slava.
Thank you. Hello, everyone. I'm going to present an overview, or most likely just bits and pieces, about climate change assessments and methods used by different researchers for this purpose. My familiarity with this topic comes from working on various projects dealing with studying the relationships between weather and weather-induced insurance losses and forecasting the effects of climate change. There are some of the research papers that we have published and provided our results, and there is also a review paper that put our work into a broader perspective of whether our methodologies are positioned in the global trend of integrating statistics and data science approaches. I also led a team of editors working on this book about quantitative evaluating of climate change impacts. The book consists of several chapters solicited from leading topical experts and presents their perspective on the assessment of climate change effects. It is astonishing how diverse the topics presented in this book, and they go well beyond insurance, where we experience the impacts of climate change. Today, my first part of the talk will be about insurance risks. So basically the left side of the screen. And then I will introduce some of the chapters just briefly, and which cover other topics beyond the insurance claims and insurance risks. So part one, insurance risks, and here I particularly focus on home insurance. Some of the relevant works in this area are about 20 years old. Remembering that insurance industry is part of the financial sector because it deals with accumulation and redistribution of financial assets, I'd like to first mention this study by Grace and co-authors who used econometric models for the insurance demand, and they concluded that price elasticity of demand for catastrophic coverage is higher than price elasticity for non-catastrophic coverage. They concluded that based on the data from the United States, for two states, Florida and New York, the results are consistent. And what it means, price elasticity, is that basically that if price changes by 1%, the people would likely hold on to their insurance on non-catastrophic losses than to the coverage for catastrophic losses, which they can drop, for example. Why it's so, and does it make sense? So for catastrophic losses are rare, right? And you may say, well, the research shows that people are not very good in estimating very low probabilities. In particular, we tend to overestimate low probabilities of positive outcome. That's why there are still so many people buying lottery tickets. But actually, in this insurance example, it sort of makes sense, the people's behavior. In fact, when we aggregate insurance data over a big territory, or such as a big country, or looking globally as much as we can, we will notice that normal extreme weather, normal bad weather, cumulatively has led to more losses than catastrophes. Yes, it's fun to watch the news about hurricanes with all the thrill and minute-to-minute updates, but the so-called low individual but high cumulative impact events still bring more cumulative losses to the insurers. And another thing to mention is that catastrophes are often covered by so-called reinsurance. Those are really big companies which insure the insurance companies. So they're like a second layer of insurance. Whereas low individual by high cumulative impact events are not covered. So the whole burden of these events lies on our local insurance companies who sell the insurance policies. So yes, the rains and winds don't usually take to the news, but you should keep your insurance coverage for these events. The next study, Press used a regression model to model financial outcome of several companies based on weather. And in this research, whether it's not specifically on damage of property, I put it here because the author specifically suggested to look at non-catastrophic weather. And that's important because people started to understand and started to model non-catastrophic weather. It again doesn't bring so much buzz to the news, but it's very important in assessing the financial outcomes and the risks. With the climate change, and as we have seen in the previous talks, with the climate change assessments, with the projections, with climate models, we expect, of course, to see more extreme weather, which will be characterized by high winds and more frequent and more severe rains. The next study by Fries and colleagues also used United States data, and they looked in more details on different perils and further classified non-catastrophic weather risks into separate groups. Based on the US homeowners data, they showed that wind damage is wind and water damage are the most frequent perils, whereas hail damage has the highest median damage. From these perils, from these three perils, water, wind, and hail is probably the least predictable. It's very hard to localize, to have very good local predictions of hail. So even with increasing quality of weather forecasts and climate projections, we still experience challenges with hail estimation. In turn, water and wind damage are more ubiquitous damages, and the models are usually better in forecasting precipitation and high winds. I've started mentioning some of the models, so here I cannot just skip the statistical part of this talk. When we have the data on insurance losses and related variables, we will be trying to model the risks, Y's, as a sum of some explained variability, mu, and unexplained variability, epsilon. We also often call this unexplained component the residuals. One simplest way to continue with this model is to model the risks as a linear combination of predictors, for example, weather variables. It could be precipitation, wind speed. It could be the precipitation in the previous day, precipitation in the previous week, etc. And coefficients beta that scale up the effects of these covariates on the risks. So this is the most simple model. Again, X here is a matrix, so it can contain multiple variables. We are flexible to include additional variables. However, this model has a number of limitations. One of them is that the relationship relationships are assumed to be linear. And another is that the residuals epsilon are assumed to be normally distributed. And insurance data are nothing but normal, or everything but normal, sorry. So they often show us so-called heavy tails, the same as incomes, people's incomes, or prices for the house, on the house. We have a large number of relatively small observations, and we have quite a few observations which are very high. Same as we have very rich people or very big houses. So we have very large losses in insurance or very high number of claims. So to model these non-normal distributions, we can apply a next class of model called generalized linear models. Here we generalize our distributions to a bigger class of distributions from not just normal. And we will apply specific transformations denoted here with the letter G to transform the data. So technically here we will be modeling, for example, not the mean of, or not the expected value of the normal distribution, but we will be modeling the expected value from some heavy tail distribution such as negative binomial distribution. And we will still use the same explanatory variables such as precipitation, wind, etc. After applying the transformation, we still are limited by the assumption that the relationships are linear. The next step in the feast of statistical models is to relax this linearity assumption. So we will keep our transformations, but we will also allow at least some of the variables to be non-linearly related to the risks. And here they're denoted, the nonlinear transformations are denoted with some functions, f1, f2, f3. These are nonlinear functions. We don't necessarily know how they look like, but we can approximate them. The very popular method is to approximate them with simple smooth functions. So imagine if you have a simple function and you can fit this function locally and locally and shift it many times and then add the results together. So you'll get an approximation to a more complex function, to a more complex relationship which you observe in the data. And interestingly, that we can apply these approximations to individual variables, like here some x1 and x2 can be precipitation. We can also apply these transformations or functions to interactions of variables. For example, precipitation and temperature could play a combined effect. And we still may have variables which preserve just linear relationships with the data. And of course, we can go even more complex. Here we have been modeling the mean risk, for example, mean losses, mean number of claims, but we can use separate equations for each parameter. So we can model the location parameter or the mean, also the scale, the variability, and also shape parameters of the distribution. And that it would be generalized additive model for location, scale, and shape. So this is the most common statistical methods, regression-based methods, which are used to relate. It could be financial outcomes, could be the outcomes that represent risks to the weather variables. Many forecasts or projections that we deal with, they will operate with these models. And imagine instead of the observed weather variables, which are represented by X as here, we will just plug in the projections from climate models. So this is the general framework for assessing what would be the outcomes or risk scenarios in the future. The climate models are estimated or ran under different climate scenario. You probably are familiar with business as usual scenario is one of the popular if we continue emitting the greenhouse gases as it's going now, or different scenarios when the emissions will be curbed. So under these scenarios, we will have different forecasts of weather variables which can enter our statistical models. So where the data science methods come to life. Data science, so here in the top corner, I copied this definition from Wikipedia because everybody understands data science differently. There are many definitions. Wikipedia defines it as an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge in a broad application domains. So what it means is that we have statistical models, but we will likely also need some algorithms, and we will also likely need expertise from the data domains to tell us what we are doing. What it means for me personally is that I should be in love with data. I should know all the details of the data, and I should also collaborate with a researcher who is much more familiar with data than I am even. So if we're talking about data science research in climate, means that we need a climatologist on the team, means that we will likely also need a programmer on the team who will help us to design and implement different algorithms. So algorithms help us to find solutions and implement our statistical models more efficiently. Here I have an example of two algorithms we applied to insurance data. Those were data from Norway. Norway is a great example because they realized long ago the need and the benefits of collecting and sharing data. So insurance companies are reporting the data, and the data are publicly available in aggregated format by counties, I believe. So we're analyzing here two counties in Norway, Østfold and Sør-Trøndelag. And we looked at the relationships between number of claims, number of insurance claims per day, and precipitation. we use two different methods coming from machine learning, or even at the border of machine learning and statistics. So I would say data science methods to find thresholds. Remember, I was saying that linearity assumption in statistical models is actually pretty restricting. If we have zero precipitation, and then we increase precipitation to 1 millimeter per day, it doesn't necessarily mean that we will have the same increase in number of claims as we are experiencing when the precipitation rises from 10 to 12 millimeters per day. So there is some non-linearity in the relationship. The method of classification and regression trees is a tree-based approach, which takes all the data we observed on precipitation and number of claims and tries to separate the insurance data, number of claims, based on the predictors. In this case, it automatically selected the threshold of 12 millimeters per day, and we have this decision tree saying that if the precipitation is below 12 millimeters per day, we will likely see 0 claims per day. Otherwise, we will see 0.6 claims per day. So this is a very simple decision, but it already tells us that there is something going on at about 12 millimeters per day. Possibly, if we are looking at predictions for the weather, we will be concerned when we see that the forecasts tell us that this will be a precipitation above 12 millimeters per day. A similar threshold we found for another province. For another county. When we applied a different method called alternating conditional expectations, this method looks for transformations of the variables that maximize correlations. So if we look at precipitation and number of claims, how can we transform precipitation in order to maximize the correlation with number of claims? So on these graphs, we see the observed precipitation on the horizontal axis and transformed precipitation on the vertical axis. I think the second plot is even better because it shows that basically when we are in the area of precipitation of 0 millimeters per day, 5, etc., 8, up to probably 9 millimeters per day, there is almost no effect on the number of claims. But after certain threshold, marked here with a red star, we observe a clear and increasing effect. So as the precipitation increases, the number of claims increases almost linearly. So both these methods, they are used iterative processes to come up with the thresholds or come up with these nonlinear transformations. So, and they enhance our statistical models in many ways. First thing we can do is we can omit data which are below the thresholds because they are not as important. They're possibly just noise. In our actual data we used for Canada, we of course observed claims, insurance claims, when precipitation was very low. Again, it could be the data artifacts, it could be some mistakes in classification process, because it could be still a weather damage classified by insurance company, but sometimes it could be a weather damage from a leaking dishwasher, or sometimes it could be weather damage which was unnoticed for a long time, and then people just came up with some approximate date when there was no precipitation. So this thresholding helps us to incorporate it into the models. How we can incorporate it into the models and how we can apply it to further estimate the change in the risks. I don't want to imply that we always have an increase actually in the risks. In some of the cases we saw decreases. So how can we estimate the change? We came up with several methods to use these thresholds we identified and then to plug it back into the statistical models to get those estimates. Because, for example, when we look at the distribution of precipitation, it looks approximately like this. We have a high frequency of very low precipitation days, and again, the distribution is heavy-tailed to the right. We have some days with heavy precipitation. Here, dk is the threshold we identified. And of course, we can just calculate the proportion here to see how much from all days we have the precipitation above the threshold. But the proportion doesn't have the same unit of the variable that we used in the model. So we need to preserve the units. We need to have the same units as millimeters per day to plug it into the model. So we designed a couple of different approaches presented in these papers to basically numerically integrate the tails of the distributions. But it's a fancy name, but the idea is the following, is that we separate the tail of the observed and some forecasted distribution. For example, the distribution that comes from the climate model. We separate the tails into many small bins, then calculate the frequency within each bin, the numbers, and then find the differences and also find the and also multiply them by actual centers of those bins. So in this case, since we will be using the centers of those bins, so they will be in the same units as millimeters per day or whatever variable you are using. So then we were able to plug back the estimates into the statistical models. It turns out that also that it's easier statistically to estimate number of claims than losses for various reasons. Again, losses are even more heavy-tailed than number of claims. Also, we don't always have information on the price of the house, on the insured amount, all those variables that determine the amount of loss. And there are several algorithms, again, that help to approximate losses. One of them is presented here. It's a two-step algorithm. So first, we estimate the number of insurance claims per day. These are data coming from 4 Canadian cities. For security purposes, we just label them A, B, C, D, because those were real data. And we see observed data marked with bars, and the fitted distributions are marked with curves. So we use this Sichel distribution, which is used for many economic data with heavy tails. And we see that in some cases we have a good fit, like for CTC, we model the observed data very closely. In some cities we miss a little, such as for CTB. Nevertheless, this fit is much better than if we would just model losses. So the next step is we have the model for the distribution of claims currently. Then we can use the tail comparison approaches to shift this distribution to the next 10 years, for example, in the future. And then we will know the distribution of number of claims, for example, in 2030 to 2040, the years. And then we can use observed claim amounts to sample randomly and then to come up with the distribution for the claim amounts in the future. So by repeating these 4 steps, we were able to project the amounts into the future. Of course, when doing all these projections, we should take them with a grain of salt, because all the modeling and forecasting assumes that the relationships stay the same, that, for example, we don't suddenly all move out from the coastal areas to the mountains, and that we don't suddenly implement a new technology, or that we don't suddenly stop insure the property. So basically these methods don't account for that, don't account for the sudden changes in policies. How can we compare different methods when we are not sure which one is the best? Here again, data science methods are used, such as different cross-validation techniques. When we have large enough data set, for example, we can say for 5 years, if we have data set for 5 years, we can design so-called k-fold cross-validation. So we can separate the data into different folds, and in so-called validation fold will be left aside, whereas we will be training our model, so estimating all the coefficients and studying the relationships on the gray data, and then forecasting for the validation fold. And we will be able to assess the performance of the model, calculate errors, etc. Then we will repeat this for the next fold, etc. Every time the gray data will be used for training and the color data will be used for validation. As a result, we will have a common performance or average performance over the data. There are other methods in cross-validation, also leave one out cross-validation, assuming that we are leaving only one observation out, not a chunk, not the whole year of data, for example. There is also validation technique where we separate the data into necessarily previous and future data, especially when we have strong trends and dependencies in the data. In general, we are trying to select cross-validation technique, which is similar to our task for the model. If the model needs to forecast in the future, then likely we will design the cross-validation in such a way that we train on the past and then forecast on the future. And using the known data for for our task, we will be able to evaluate the performance. So this is an example of the flowchart in general, what I have been talking about, how we work and how we incorporate the data. So first we use observed daily data, for example, for number of claims or losses, and then observed weather conditions. And then we do the attribution analysis, so basically regression modeling. We can do comparisons, we can then forecasts. When we do forecasts, we employ daily projections of weather conditions from climate models. And then if we do a two-stage forecasting, then we use the claim-by-claim losses to apply in the algorithm of simulating the next losses. The data, as you see, come in all stages of analysis, and data quality and quantity are very important. In one of the papers, we ran a scenario of different data usages. The reason for running this analysis is that for the current data, we can use observations from weather stations. For example, we use long-term observations from around airports, because those are usually weather stations which have the longest records. Or we can use model data. So when the climate models are evaluated, they have so-called evaluation runs in the recent past. So we can use the gridded data from climate models to do the attribution analysis, basically, to feed our statistical models. Why it matters? Because for the future, we have only model data. So it might be the case that it makes the difference whether we are comparing model with model or model with observations. In our analysis for 4 cities, we ran these 3 scenarios where we compared model with model, model with observations. And we saw that in general, for this example, the conclusions agree that there will be a general increase, for example, for the number of claims in all cities. And actually, the magnitude also is very similar across cities. However, the results are not always that good, not always agree that well. Some of the results we obtained are very different based on the different climate projection we are using, or based on different climate model. So as you're aware, different climate models come from different research teams, and they are best in their country usually, and they are all aggregated by Intergovernmental Panel on Climate Change, by the projects of Climate Model Intercomparison, CMIP. But models don't always agree. And sometimes we observe that the greatest difference comes from different models, not even from different scenarios of climate. So there lies a lot of uncertainty in the future risks as well, because the uncertainty of the models percolates or propagates into the uncertainty of our statistical forecasts. As someone clever said, it's very difficult to make forecasts, especially about future. However, there are different methods These are some of the methods that are actively used right now. Statistical machine learning methods, which help us to address the uncertainty and have better understanding on the future risks. I'm not saying that everything will be bad. I just want to have a better estimation of the risks so people are aware. From the models list and the methods listed here, probably regression models are more popular, and the models such as deep neural networks, random forests, they still have a lot of potential in the applications. I think they were not so widely applied yet because of the interpretability issues. Those models often act as black boxes, and it's very hard, for example, for insurance company to base their decision on pricing insurance risks if they don't know exactly how the results are obtained, if they don't see exactly how the numbers played out into a certain answer. But overall, I think the increase in data availability, data quality, and in statistical methodology will help us to improve the insurance products and inform public about the change in insurance risks. Again, it's all about compromises, right? So it's not necessarily that people will have to move out from their homes close to the ocean. It means that they will be likely paying more. It's the same as, for example, choosing what to do on the weekend. You can either jump with a parachute or spend a day in the museum. The risks are different. The prices are different. You are free to choose. So the same if you are buying a house, you might consider buying it in a landlocked condo, or you can consider a beach house, right? Again, the risks and price are different. As the second part of the talk, I'd just like to go and introduce some of the chapters from the climate book that we published. Again, they were solicited from different experts, and some of the other aspects where we see the impacts, some of the other topics where we see the impacts of climate change. Of course, fires, the wildfires, and here the authors used extreme value distributions to model the fire weather index. Of course, we have the problem of high tide flooding. Maryland has lots of coastal areas which are subject to that. Here, the researchers used regional ocean modeling, satellite data. They made projections for Annapolis, Baltimore, and presented their results, again, dependent on different scenarios of climate change. Also, climate change impacts biodiversity. Here, our researchers, Ryan Woodland and Jeremy Testa, used GAMs to model generalized additive models to model biodiversity indices and see how they change and might change again with the climate change. Of course, climate also impacts other climate-sensitive industries, for example, electricity and, in general, energy sector, energy consumption. So in this chapter, cost-benefit analysis is used to showcase what are the potential benefits we can get, how many times we can save if we implement certain measures against climate change, certain adaptation measures. I participated myself in the chapter on studying the impacts of weather on traffic accidents. We didn't do forecasts far in the future, but we used very good data set from Mexico City and studied the relationship using random forest techniques and again, generalized additive models. This was our workflow of analysis. Again, like many data scientists, we collected the data, we split the data into training and testing for validation. In the training data, we estimated two types of models, generalized additive models and random forests, and then we used them to predict number of accidents for the test and set. Again, the test and set, the number of accidents was never used in modeling, just the weather data from this period was used. And then we compared the predictions with real ones. Interestingly, the machine learning approach of random forest was very accurate. So this is the period for which we held out as the testing period. These were the observed number of accidents in the city, and these were the predicted by random forest. So you can see they're very close to the observed ones. Of course, if we again try to make predictions for the future from today, we will have an additional uncertainty about the future weather. In these predictions, we knew the weather for certain, but we don't know the weather for certain for tomorrow, and for sure not for 5 or 10 years ahead. But with those models, we could study the relationship between different variables. Here I'm showing the results for interaction effects. So we could see that the numbers represent the number of accidents per 100,000 vehicles. And here we have the rainfall and temperature. And we see that the highest number of accidents happen when we have near freezing temperatures with rainfall, or high rainfall and high temperatures. So we could use this information if we want to make predictions, or again, if we see predictions for the future weather. Of course, Mexico City is not subject to very low temperatures, so we didn't see below freezing there. And of course, the last topic that I kind of left out is the relationship of climate with agriculture. Agriculture risk management is very important, but it's also probably one of the oldest research topics. As long as the agriculture existed, there have been many different approaches applied. Risk assessment in agriculture often depends on our ability to forecast yields, and there have been many wonderful research papers trying to forecast yields. In this chapter, again, from our book, the authors used integrated modeling and socioeconomic analysis, trying to bring all the information that we have access to about future climate, about different policies, about trade policies, to model the risks. Overall, in the future, I think the research will move in the following directions. First, of course, we will need improved data, bigger sample sizes, improved quality of data. We will see more application of machine learning and artificial intelligence approaches. I think people will trust them more, hopefully. We will also need to emphasize joint modeling of variables, so such as the interaction effects of variables, not just one or two, but even more coming together. Also, integrative approaches are very important because as climate changes, also our behavior changes, and also we have some innovations that can help us to adjust and to adapt to climate change. And we should also use this information or our scientific guesses about that in our future projections. And another important topic for future research is improving regional models, because many climate models are good in projecting the overall climate change, but if you look at the small scale, for example, a county or a city, we still have lots of room for improvement. With that, I'd like to thank my co-authors, co-editors, AMSI's colleagues, and funders who funded parts of this work, including University of Waterloo, Canada, actuarial societies. Also, some of the grants from NOAA and NSF allowed me to work on climate-related problems. So thank you, and thank you for your attention.
Thank you very much, Slava. While we wait for questions to come in, just a comment from me. I wonder whether you can give us some sense of by how much larger the non-catastrophic losses are to an insurance company compared to the catastrophic. I must admit that surprised me a little bit.
I'm sorry, I don't have the number on top of my head, but I remember the reference that we cited when we wrote one of the papers. I can provide that.
Is it by a little bit, or is it sort of substantially more for chronic loss compared to catastrophic loss?
I would say, like if you put me to the spot, I would say like 40 and 60%.
Okay. Okay, that's fine. I just, as I say, that just really surprised me that you think of this acute loss that occurs under catastrophic storms as really dominating the insurance risk, because that's really what you hear about on the media, right? It's not, as you say, that it's just the minute-by-minute update of spaghetti plots. It's the talk of how many billions of dollars State Farm has lost or other insurance companies have lost when these storms crash into heavily developed coasts. And so I must admit, I found that fact very surprising, that that sort of chronic losses add up so much. So let me follow up with another question, Slava, and this really relates to the methodology. It strikes me that the methodologies you've presented are, as you said, making predictions, particularly about the future, is really hard. Do the insurance companies take these kinds of approaches when they look at their risks, or do they take a different approach when they try and calculate longer term risks?
That's a wonderful question. I think the first project that I started to work on in Canada on home insurance was actually the company looking forward to adopt these approaches that would account for climate change, because they have been pricing the insurance based on the past observations, right? So what's the probability that a certain house will be experiencing losses, and what will be the resulting amount? But with the climate change, they experience or they're subject to more losses. So basically, the company is losing money, and basically, not to become bankrupt, they need to make the adjustments.
Yeah.
So I think it's undergoing process right now.
And you also mentioned about the uncertainty in your predictions based upon the climate scenarios being more significant than perhaps the different statistical models that you used.
Right.
And you think that's likely to continue, that the climate uncertainty will still be the biggest challenge in all of this?
I think so. We definitely value the diversity of different models, right? Because they're presented by independent research teams, and they all have their point, they all have value, they all the projections we have been using, they all come from climate model inter-comparison project. So they're all, the model are all like vetted, they're all checked, but they still disagree, and they can disagree also just by or due to the climate stochastic components, because small changes sometimes result in like a global changes, you know. So every time they run climate model, it gives slightly different results.
And I assume that becomes particularly true when the insurance industry is really interested in downscaled climate models. They really don't want to know what's going on at the global level. They want to know what's going on in Poughkeepsie rather than you know, at the US as a whole. They want very specific.
Right, absolutely. And as we're trying to make it more precise, the uncertainty rises as well.
Yeah. All right, well, keeping an eye on the time, Slava, thank you very, very much for your presentation this evening. For those in the audience, I want to thank you all, particularly those of you who've been with us for all of our 6 presentations this autumn. It always is events that mark the changing of the seasons for me. We started this seminar series and it was still light at the end of the seminar. We end this seminar series and it's dark before I get into the room. So once again, thank you for your company over the change of the season this autumn. A thank you to all of our presenters. A reminder that all of these presentations are available on our website, which you can get to through www.umces.edu. And we look forward to seeing all of you in the spring when we will begin to learn about the urban ocean. Thanks all very much and good evening.